Alright, how's it going? I only see 2 Halloween costumes. Sad. Oh well. I usually dress up for Halloween, I just didn't have the energy this year, but maybe I'll dress up some other day. Questions?
So, for PA3, so if the user, in the argument line, if the user types 100 AB, how can I get 100 from 100?
So if the user types 100 AB, that's an error, and I think I said to exit in that case. So let me actually pull up the assignment. It's been a few weeks. Oh, if an argument is given, you may assume it's a positive integer and ignore any additional arguments. So you don't have to error check. They're not going to say 100 AB. They're going to say 100.
So another question is, how can I use scanf in back?
You can't.
I can't.
But would you need to?
Like I want to check if 100 AB is acceptable, how can I get a...
So you have a script called HL, right? And if somebody runs it by saying HL 1000, okay, there's 2 things. First, there's a variable named $number sign. Okay, that's a variable. And let's just try this.
You said we don't need to check for extra input focus, correct?
I think that's what I said. If the user runs HighLow with an argument, if an argument is given, you may assume it is a positive integer and ignore any additional arguments. So if there's an argument, assume it's an integer and just proceed with that. So I'm just going to print out an echo statement. Let me do it like this. $number is, and let's just print out the value of $number. So if I just say HL $number is 0, it means there's no arguments on the command line. If I say HL 1000 $number is 1. So that tells me that I have an argument. And that argument is in the variable called $1. So if $number equals 1, I'm going to say echo the argument is, and I'll show you the value of $1. So if I just do HL, $number is 0. If I say HL 1000, $1 is 1000. So this variable right here, $1, gives you the value of the argument, right? But you only want to use that if $number is equal to 1. If $number is not equal to 1, then $1 is going to be blank because there wasn't an argument given. But I can do whatever I want with that $1. I can say max equals $1, and now max is a variable whose value is going to be whatever that argument is. And I can say something like max equals $max. So if we're thinking C, $ number is like argc, but it's -1, and $1 is like argv bracket 1, $2 is like argv bracket 2, and so on.
Yeah, I mean in C you can use scan I to get 100 from maybe 100 AB, right?
Right.
But in Bash you cannot do that.
But you're not going to get 100 AB. Right? I've said I won't use that as an input.
Yeah.
Now, if you really wanted to do that, you got to do some work. Right, so if it's 100, well, I did AH, but if it's 100 with some extra stuff after that, you've got to do some work. Yeah, this isn't worth. Right, so I'm only doing this as a teaser. Okay, so that'll get rid of the stuff after the 100. So we'll talk about set and regular expressions in a few weeks, and we'll see why this works to pick off the numbers in the beginning and throw away everything else. But this is why I said, this is one of the reasons I said don't worry about it for PA3. So I won't give you anything other than either HL with no arguments or HL followed by just a number. And nobody reads this stuff, by the way. It's easy to write once you know it, but it's impossible to read. So you write it and you hope it works. All right, good. Other questions? All right, so let's so make sure program 3 is submitted on time and that it's in Git and it's readable by me and all that stuff, as usual. All right, so let's talk about PA4. PA4, we're back to writing C code, and it's not a C version of HighLow. It's a totally different program. It's an index program that you can run on a set of text, and it will basically tell you a list of all the phrases that occur in your text file and how many times each one occurs. And it will be sorted in increasing length of each phrase. So it's a big long C program. it will take you a while to complete it, so you really need to start it earlier rather than later. Submit it through GitLab as usual. I want your GitLab repository to be named index with an uppercase I. Okay. And set me up as a reporter as usual. So this is a 2-page assignment. So we're getting more ambitious. Okay, so what's the basic setup? You're going to write a program that's going to read text from standard in. Okay, so something like fgets. It's going to take that input and it's going to break them into what we call phrases. So a phrase is roughly a sentence or a piece of a sentence. Something, comma, something, that's 2 phrases. So commas and semicolons and stuff like that will mark the end of a phrase, as well as a period. So you're going to break the input into phrases, and you're going to keep track of all the phrases that it finds in the input and how many times a phrase occurs. So you're going to build basically an index of sentence fragments. And this will go on until it hits the end of the input. And then you go ahead, you sort your phrases, you print them out with the number of times each one occurred. And so let me show you what this looks like. So there's sample code on the Linux server under /temp/index-sample. And so I can put some text into here. I misspelled fun, but that's okay. All right, so here's some text. And hello appears twice, and this is fun appears twice, and the other things appear once. So I hit Control D because I'm coming in from the keyboard. So Control D says end of file, and this is what it generates. So hello appeared twice. Is this un was once. This is fun was twice, and again I say hello appeared once. And everything gets converted to uppercase. Okay, so uppercase hello, lowercase hello would be the same thing, and so on and so forth. Okay, so the details are numerous and long and confusing, but we'll break it down piece by piece. So details, first thing, convert everything to uppercase. Okay, do this as soon as you read something in, turn it in uppercase before anything else. And then you never have to think about it the rest of the assignment. Okay, if you don't do that, you're going to find yourself doing this again and again in different pieces of code. It's going to trip you up. So first thing, read in your input, switch it to uppercase, and now you can forget about the first detail. Second thing, all white space should be changed into a space, or into spaces. So if you get a new line, if you get a tab, just change it to a space. If you get 10 spaces, it's just 10 spaces. If you get 10 new lines, that should be 10 spaces. If you get a space, a new line, a tab, and a space, that should turn into 4 spaces. Okay? These are simplifying the input so that you can process it more easily. So second detail, anytime you get anything that's a white space, change it to a space. And there's a macro called isSpace that you can use to know if you've got white space. So do a man on isSpace, you need to include ctype.h right here. And then if you look for the isSpace documentation, checks for white space characters. So space, form, feed, new line, carriage, return, horizontal tab, and vertical tab, any of those will come back with true from isSpace. And there's also a function called toUpper, also in ctype.h. toUpper, you give it a character, it gives you the uppercase version of that character. If it's already an uppercase character, it just gives it back to you. If it's something like a number or punctuation, it just gives you back this thing that you gave it. But if you give it a lowercase letter, it'll give you back the uppercase. So when you read a character of input, pass it through to upper, okay, get an uppercase character, and then run it through is space, and if it's a space, just change it to a single space, quote, space, quote. And now you've got the first two details totally taken care of. Third detail, certain characters you ignore, parentheses, single double quotes, and a hyphen. Ignore them, they don't exist. When I say ignore them, it doesn't mean treat them like a letter. It doesn't mean do something else. It means completely ignore them, take them out of the input. Okay? If someone hands you a quote, just burn it. Throw it on a pile of something and get rid of it. Okay, they do not exist. So now with those first three details, we've got some cleaned up input. All the letters are uppercase, all the spaces are just a space, and it doesn't have any of these funny characters. Okay, so we have to define what a phrase is. So there's this set of 6 magic characters. There's a comma, a period, a semicolon, a colon, a question mark, and an exclamation mark. So a phrase begins with any non-space character other than these. A phrase ends with any of those 6 characters. And everything in between is part of the phrase. So our usual example would be something like, hello, period. This is a phrase. Begins with the non-space character other than punctuation, and it ends with the punctuation. So HELLO is a phrase. Can, comma, won't. Okay, convert it to uppercase. Ignore the quotation mark. There's still a period at the end. So your phrase begins with a non-space character and includes everything up to one of those magic characters. So can is a phrase. Okay, next phrase begins with a non-space, non-magic character. So that's not the start of a phrase, that's a space, that's not the start of a phrase. W is a non-space, non-magic character. That's the start of a phrase, and it goes until you get to the period. So that's the next phrase. All right, this is fun, comma, space, no, question mark, uppercase. So what's our first phrase? Starts with a T. It can include spaces. It ends with one of the magic characters. That's your first phrase. Next phrase begins with a non-space, non-magic character, so it's not the comma, it's not the space. It starts with the N. It ends with the O, because question mark is a magic character. Okay, it's not a perfect rule, but logically, if you just kind of think of pulling out sentence fragments in a reasonable way, this gets you most of the way there. And if your sentence happens to run from one line to another, right, if I have something that says this is, and then there's a new line, and then fun, remember you change that new line, that's a white space, you change that into a space, so you turn this into this is fun. Right, that's why we're changing things like new lines into spaces, so this just looks like a sentence, and then you turn it into uppercase. And now it's a nicely behaved sentence. Alright, so a phrase begins with a non-space, non-magic character. It's a collection of consecutive letters, characters, and spaces, anything other than a magic character, and it ends when you hit a magic character. And that's maybe the trickiest part of understanding the assignment is what makes a phrase, but those are the rules for it. And they don't necessarily line up with our intuition, but they don't have to, right? It's just, those are the criteria. All right, for your final output, put the occurrence count, the number of times each phrase occurs, as a 5-digit integer, including leading zeros, followed by the phrase in angle brackets. So we want something like this. 5-digit character, including leading zeros, for the count, a space, and then the phrase in angle brackets. Okay, we'll go through the pseudocode in a minute. So here's a sample input file, and here's the output that it would produce. This is just to play with, because you want to understand exactly what your code should do before you start trying to write the code to do it. So you can work with this sample file and make sure you understand why this is the output that it should produce. Okay, that's different from writing your code and modifying your code until it produces this output on that input. That's a much harder task. Okay, your goal here is to go through this by hand, work with other people, find a whiteboard, and convince yourself that if that's the input, this is what the output should be. Once you've done that, now you understand the algorithm sufficiently to actually write the code to implement it. All right, so here's some pseudocode. Read from standard in, a character at a time, until you find the beginning of a phrase. So what does that mean? Read from standard in. If it's a space, keep reading. If it's a magic character, keep reading. Okay? It's never going to be a quotation mark or a parenthesis because you're ignoring those. You never want to see those. So those shouldn't even come through your get character function. So read characters from standard in until you find the beginning of a phrase, which is a non-space, non-magic character. Okay, now keep reading from standard in until you get to the end of a phrase. And as you're reading, store what you're reading into an array, a string. After you find the end of the phrase, right, the magic character, throw a null terminator on your string. Now you've got a string containing your phrase. Okay, if you've never seen this phrase before, add it to your collection of phrases and record the number 1 for the number of times you've seen it. If you have seen this phrase before, just bump up the counter for how many times that phrase has appeared. If you've already seen it 10 times, reset it to 11 now. And just keep iterating through those steps until you hit the end of the file. Then sort the array of saved phrases by length, and then print out the array phrases with their occurrence count. Does that make sense so far? So when I say read, I have a little asterisk up next to it. So the footnote says you may want to make your own version of a getChar function. So we can call getChar, it's part of the standard library, and it will read one character for us and give it back to us. But then we got to convert it to uppercase, and we got to change it to a space if it's a white space, and we got to ignore it if it's a magic character, and so on. So I'm suggesting you make your own version of getChar, super getChar, right? And what super getChar does is exactly what getChar does, but also it will convert white spaces to a single space. It will convert letters to uppercase, and if it sees a parenthesis, a quote, or a dash, it will get another char until it finds something that's not a parenthesis, a quote, or a dash. Right? So it'll do that ignoring of special characters for you. So you make your own super getChar function, and now those first 3 details are already handled. Right? Because super getChar will always give you something that's uppercase if it's a letter, it's a space if it's a white space, and it's not one of these things we should ignore. All right, simplifying assumptions, and these are important because if you don't do these, this gets even harder, and it's challenging enough as is. So simplifying assumptions, you can assume that a phrase is 200 or fewer characters. Now you may encounter a phrase that's longer than 200 characters, but you can only pay attention to the first 200. Okay, you're allowed to ignore the rest of the phrase. But be prepared for phrases that are, 6,000 characters long. That should be okay for your code to handle, but it's only going to look at the first 200 and store the first 200. Okay. So if the phrase is longer, ignore the remainder of the phrase. You can also assume that you only have to keep track of 1,000 distinct phrases, but there could be more than 1,000 different phrases in the input. But if you've already seen 1,000 phrases and you've got 1,000 phrases stored and you see a new phrase you haven't seen, just ignore it. Okay? Don't blow up in segfault or rip a hole in reality or something, but just ignore it. Just keep going. And read more of your input, and you get to a phrase you've already seen, go ahead and bump up the tally for that phrase. You see a new phrase, ignore it, keep going. Okay? Because of these two assumptions, you can use, and you should use, statically defined arrays. So you don't need any car stars in here, in your variables. You might have them in functions. But what you can do is you can make, for example, something called dictionary. And you can define it to be 1,000 elements long, where each element is 201 characters. Okay, this is a two-dimensional array in C. And the idea is dictionary bracket 0 is the first phrase you found. Dictionary bracket 1 is the second phrase. And dictionary bracket 999 is the 1,000th phrase. But what is dictionary 0, dictionary 1, dictionary 999? It's a character bracket 201. It's a string. So each of these is a string, which is actually a character array of 201 characters. 201 characters means you can have 200 characters that are anything you want, followed by a null terminator. Since our phrases are assumed to only have 200 characters, we can store our longest possible phrase in any of these dictionary entries.
Is this how argv works?
This is essentially how argv works, right? argv is a two-dimensional array. argv bracket 0 is some sort of string, right? The difference with argv is it's dynamically allocated. So it could be longer than 1,000, right? Each of these entries could be bigger than 201. It's set up, and we don't know ahead of time how many elements are in there or how big each element is. So we have to say car star star argv. But don't do that for your dictionary, because that gets complicated. Anytime that you pass this to a function, you can declare your argument as car argument bracket 1,000 bracket 201. And it's going to make things so much simpler if you do that. If you just assume everybody in the whole space of my program knows that my dictionary is a two-dimensional array, it's 1,000 by 201. Right? If you let yourself take advantage of that, your code gets a lot simpler. Okay, and it's not the fanciest way to do it. It's fancier to do car star star, and then if you wanted, 2,000 elements, you could still do that, but it makes the seg faults just pour down like rain. So take advantage of this. And if you want your code to be really general, right, use a define. Instead of coding 1,000, just define something called, max number of phrases. Number sign define, max number of phrases 1,000, and then you can use max number of phrases wherever you have 1,000 normally. And then you can change that one define, but make your life easier. Keep it all static. Okay, additionally, this is going to be where we store all the phrases. We also need to know how many times each phrase occurred. So we can have another array, which I'm just calling count, and make that an array of 1,000 integers. And that can be totally static. And so count bracket 0 is the number of times, bless you, that dictionary bracket 0 occurred. Count bracket 0 is the number of times that dictionary bracket 0 appeared in our input. And count bracket 1 is the number of times dictionary bracket 1 appeared. And count bracket 999 is the number of times dictionary entry 999 appeared. And these are sometimes called parallel arrays, right? So we have an array of phrases and we have a parallel array of integers. And the 37th phrase appeared a certain number of times. How many times? The 37th integer in this array tells us how many times the 37th phrase occurred. Okay, so parallel arrays, common tool. If you know how to code structures and you like coding structures, you can use a structure instead. You can have a structure that contains a phrase, that's 201 characters, and an integer, which is how many times that phrase occurred, and then make yourself an array of 1,000 of those structures. Call that your dictionary. Okay, that's a simpler way to do this if you're comfortable with structures. If not, just use parallel arrays. And everything I'm doing up here is assuming parallel arrays. Alright, so statically defined arrays, dictionary is 1,000 by 201 and count is 1,000. Dictionary I stores the ith phrase, count I stores that phrase's tally. Or you can use structures. You can use things from standard I/O, string, C-type, and standard lib, but everything else you gotta write yourself. Okay, if you know how to use a hash function, you can do this in like 5 lines of code. So guess what? I don't let you use a hash function. Okay, unless you write it yourself. So no pre-built sorting or hash functions. Alright, and I strongly recommend experimenting with different input files. We'll talk about suggestions in a moment. Important and final notes. Okay, submit via GitLab, repository named index by the deadline. You must include a makefile, so we're going to go over makefiles. Okay, we'll go through that next week. Makefiles will make your life better once you're using them. But it's one of those things you've got to learn, you got to get used to doing. But once you have a makefile for this, it makes it a whole lot easier to do your development. Make sure everything is documented. You're going to have a lot of comments in your code. Okay, if you don't, you're going to lose a bunch of points because this is complex code. Right? So try to comment it as you're writing. Put comments in that make sense to you, to remind you what you're doing. Make sure you can handle long phrases. Make sure you can handle files that have more than 1,000 phrases, even though we're only paying attention to the first 1,000. So sample executable is at /temp/index-sample. That's the one we just ran. I've also put a good test file in there. It's called War and Peace. It's a long input file. That's a good one to test your code on. Right? That's one that I'm going to test your code on. So it's a easy way to throw seg faults. So /temp/index-sample. And I'm going to use this redirection. I'm going to say, instead of waiting for me to type input, let's just read the input from a file. And I'm going to read it from /temp/war and peace. And it only takes it a few seconds, even though War and Peace is 64,000 lines long and over 3 million characters. But it can index that pretty quickly. And so there's how often some of these phrases occur. So, oh, ah, no, who, but, and, yes, those all occur a bunch of times. And you can actually have some fun with this. If I take this and I sort it, because I've got leading zeros and I've got the numbers coming out in the first 5 columns, if I sort this, I get my output with increasing number of occurrences at the bottom. So the most common phrase in War and Peace is yes. The third most common phrase is no. And in between is well, which is kind of in between yes and no. Said he, she said, and so on, said she. So you can do some interesting analysis on text with this. I suspect that maybe with the first like 20 lines of this, you might be able to like classify written material into like, what's the short version of what happens in here? Is this a happy story or a sad story? Things like that. So you can have fun with this. I guess Pierre is pretty significant because Pierre said something 99 times. So that's a good test file. And there's well more than 1,000 phrases in War and Peace, right? So we're only paying attention to the first 1,000. And some of these phrases are definitely long. All right, so here's a long one. So this one got cut off at 200. The maintenance of the balance, and it just ended right there. All right, so this will exercise your code. This is the final exam part, right? This is not when you're developing your code, maybe. But once you think you've got it working, this is a really good test case to say, okay, let's see if we got everything just right. And it may seg fault. But start off with more reasonable test cases. And like I say, here's a pretty reasonable set of input that exercises the uppercase, lowercase. There's a colon to ignore and things like that. Or a colon that ends a phrase. All right, still with me? All right, suggestions. An excellent opportunity to practice modular design because there are a lot of different functions in here, and you really, really, really don't want to write this by just starting and writing code and trying to make one main program that reads your input and converts it and breaks it into phrases and tallies it, right? Your main program is just going to be huge. So start thinking about breaking it into functions. And it has 2 or 3 benefits. One, it makes your main program smaller, and it makes the things that your main program uses smaller because they're calling other pieces of code and so on. So it's less to keep in your brain. But 2, you can test these small pieces as you write them. So that once you've got your super get car written, you can exercise that, you can test it, you can debug it. Once that works, you don't have to think about it anymore. If something's not working right, it's like, wait a minute, am I ignoring double quotes the way I'm supposed to? Well, if you already put that into super get car and you already tested it, you can forget about it, right? It's just this magic get car function that happens to do exactly what you want. This is kind of the magic of programming, right? It's a world that we're creating. If I want a version of getCar that does something special, I write it, and I make sure it does something special, and now I've got this amazing tool, right? So think Minecraft. How many people play Minecraft? Cool. You know, make the tools and then use the tools and use those to make better tools and use those to make better tools and use that to build your world the way you want it. That's a programming mindset. Okay, so think about your overall algorithm, break it into a few steps and code your main loop accordingly. Then begin coding the functions to implement those steps. That's a top down. You can also work bottom up. So let's look at very high level pseudocode for index. So what do we do? Read a phrase. Is it new? If yes, save with count equal to 1. If it's not new, increment count. And go back and read another phrase. That's the heart of the whole program. Read a phrase and either save it and set the count equal to 1, or we've already seen it, just increment the count of how many times we've seen it. Okay, when we get to the end of the file, sort the dictionary and print the dictionary. hey, there's your whole program. We're done. It's like 6 lines of code. Right? So the only trick is you've got to write code that will read a phrase. You've got to write code that somehow finds out if this is a new phrase, and then something to either save it with a count of 1 or to increment the current count. Somehow have your read phrase detect end of file, and then you've got to have a way to sort, and you've got to have a way to print. But your main program is really about that long if you do it like this. So what are some of these pieces of code that you want? A way to read standard in and pre-process the characters. That's your super get car. Okay, get car reads from standard in, but do some extra stuff. Make a super get car. A way to detect the beginning of a phrase. Well, you can make a function that you give it a character and it says, is this the beginning of a phrase? How do you know? Is it a space? If it is, it's not the beginning of a phrase. Is it a special character? If it is, it's not the beginning of a phrase. If it's anything else, it is the beginning of a phrase. So that's a function that's a few lines of code. You give it a character and it gives you back, a 1 or a 0. 1 means the start of a phrase, 0 means it's not. A way to detect the end of a phrase. Well, that's almost the same, except spaces don't end phrases. End of a phrase is just one of those 6 magic characters. So take a character, if it's magic, say yes, that's the end of a phrase, otherwise say no. Well, if you take those 2 routines and you use them inside this little pseudocode up here, right? That's just a few calls to your is it beginning a phrase, is it end a phrase function. And in between, right, as you read things from standard in with your super get car, you just have to stick them into an array. And you've already done array manipulation in your last week's ODPs, right? Have an array start off with its length being 0, and when you get a character you want to save, just save it in that location, bump up your output location. Keep doing that. Every time you read from super get car, you save it in the next spot in the array. And when you find the end of the phrase, now just write a null terminator at the next spot in the output. So you've done pieces of this already. You're just going to use that with this phrase cognizance, and that lets you create a phrase. And then you need a way to store it in the dictionary, either as a new entry or as an additional tally. So you can make this one function call. Read a phrase, and this could just be a record phrase. And then go back up to the top. And your record phrase is actually going to do this. It's going to look for your phrase in your dictionary. If it finds it, it'll bump up the count. If it doesn't find it, it'll add it as a new entry in the dictionary. So a lot of work to do on paper before you start writing code, right? You want to think about what the whole program has to do. You want to start writing some pseudocode, and then think about what you're going to put into different functions. What do I want my main program to do? It's going to call a bunch of things. What are those things it should call? And then those things, how are they going to do what they're supposed to do? What does my record a phrase function do? Well, it's got to somehow search my dictionary to see if this phrase exists. Well, maybe I'm going to write a function for that. And I'll just say, if search parentheses dictionary comma phrase equals 1, then increment phrase comma dictionary, right? Otherwise, store phrase comma dictionary. And so those might be 3 or 4 separate functions. So really spend some time playing around with this. Okay, and this is a big part of what I want you to try to get out of this assignment, is this idea of how do I break my code down into smaller pieces? Because that's an essential piece of programming. Anything really large is how do you modularize? And there's so many different ways you can divide this thing up, right? So and none of them is more right or wrong than any other way. But spend some time with it, and this is something that you're welcome to work with other people on, right? Share some ideas. I thought about making a function for this. Does that seem reasonable? That kind of thing. Definitely make a separate function for sorting, because that's a nice piece you can just cleave off really cleanly, And you can test that, just hardwire a dictionary with some stuff and pass it to your sort function and make sure it works. And we'll talk about sorting next week. We'll go through a bubble sort. You've done bubble sorts before, I'm pretty sure. But we'll review that. That's a pretty straightforward sort to code up in C. And then a way to print is really just a for loop with some formatting. So %05D will print a 5-digit number with leading zeros. So that's the whole magic for making your count appear the way it's supposed to. And then space, angle bracket, %S, angle bracket prints out the phrase in brackets. So that's just a for loop with the right type of printf. Okay, so we will talk about makefiles. We will talk about bubble sorts. We will start some ODPs next week that do more string manipulations to keep us up to speed on strings. But that's basically your PA4. So questions at this stage? Yeah.
Are we able to compare, I think we can, but we're able to compare strings to strings, correct?
Correct. So there's a function called string compare, strcmp, and you definitely want to use this. So string compare takes two strings and it gives you back an integer. If the strings are the same, it will give you back a 0. If they're different, it will give you something different from 0. Okay? It's not going to give you back a 1 if they're different, but it'll be non-zero. So to know if two strings are the same, you can say something like if parentheses string compare s1 comma s2 equals 0. This tells you that they're the same. And if you say if s1 equals s2, that's not going to compare the strings. Okay, so for strings you can't just use double equal, you got to use string compare. What string compare does is it actually goes through character by character and compares each character. And if any characters are different, or if the length of these strings is different, it'll return something non-zero. And then you know they're not the same. So string compare, it's in string.h, and you can read the manual page on it.
Just to clarify, this would be something we could legitimately use though?
Yeah, so you can use things from string.h, including string compare, string length, string cat, probably the three that you would use. Mainly those first two, string length, string compare. But it might give you an ODP where you write your own version of string compare. All right, good. We are 10 seconds over, so I'll let you go. So, final reminder, no class tomorrow. I will see you on Monday.